Today we are going to be interested in studying the Laplace transform. The Laplace transform, which was coined by mathematicians after they concluded that Laplace was effectively the inventor of this transform, is very, very useful to deal with functions of time in ways that are convenient from a computational standpoint. In short, the Laplace transform takes functions of time and spits out functions of frequency. These functions of frequency are, in general, very easy to manipulate. When the original functions of time were generated by the kind of dynamical systems that we will study later on. It is therefore not a surprise that Laplace transforms have remained exceedingly useful, not only earlier this past century, but also now that computers have taken over our daily lives. In order to move on, I need to access my notepad. And so let me exit the full screen and begin with my notepad. So, the Laplace transform begins naturally with functions of time. Okay, and so we will take a function of time. We will begin with a scalar function of time, f, which takes time and then spits out for each time f of t. Okay, and again we assume that f of t is for now a real number. The function, the Laplace transform of f, so the Laplace transform of f is denoted L of f, like this. Okay, and we have that L of f is equal to the integral from minus infinity to infinity of e to the minus st f of t dt. In other terms, the Laplace transform of f is a function of s, the variable s. Okay? And it is that integral. You have several ways of interpreting this, and I will discuss them later. If we are to look at the Laplace transform further, okay, then we can say that the Laplace transform of f of s is a complex number, okay? So for each s, L of f of s, which we sometimes call f hat or f, or sometimes with a big abuse of notation, f of s. So this Laplace transform takes a complex number at the input and spits out a complex number at the output. This Laplace transform enjoys enormous properties. Before I go for the fancy properties, let me start for simple ones. Many functions f take time beginning at 0 and going to infinity. In other terms, there's an initial time, in which case the integral from minus infinity to infinity of e to the minus st f of t dt doesn't make much sense. And it makes complete sense to then look and change the bounds of the integral by replacing this guy by 0. And so we obtain the integral from 0 to infinity of e to the minus st f of t dt. Okay? However, sometimes we will encounter functions that map. So let me change the color here. So functions f that takes t going from minus infinity to infinity. Such functions exist. Okay, I can plot their graph like this, and they are just functions that have no beginning and no end. Okay, minus infinity being here, infinity being here, and t being the variable here, while f of t is on the y-axis. Okay, and in this case, indeed, the Laplace transform of f is the integral from minus infinity to infinity of e to the minus st f of t dt. Now, what we can do is realize that a function f which takes time from 0 to infinity, okay, is equivalent to a function g that takes time from minus infinity to infinity, and we can say that g of t is equal to 0 when t less than 0, and otherwise g of t is equal to f of t. Okay, and so that allows us to basically map everything together and obtain a single operational framework for the Laplace transform. Now it is time to talk about the various interesting properties of the Laplace transform. So for now, let's try some examples. So some of these examples may include various test functions. One of these test functions could be a step. Okay, so how does a step work? I have the y-axis here, the x-axis here, I have 0 there, I have minus infinity here, plus infinity there, and I have 1 here. Then the plot of the function goes as follows. Let me get this, okay, and change the function. Oops. Let me change that function. Boom. There we go. The function is 0 for negative values, jumps to 1 after time goes to 0. So that's why it's called a step. Or it has other name. I think one of them is Heaviside function. Okay. So let's now compute the Laplace transform function of a step. We need to compute, so we call the step s of t, maybe st of t, to change it from the variable s, and we get that Laplace transform of st is equal to the integral from 0 to infinity of the value of the step function there, which is 1 times e to the minus st dt. Now, let's see when this integral even makes sense to be computed. This function, in general, doesn't behave very well. Okay, look, s is equal to a plus j times b. Okay, so I can rewrite my integral as integral from 0 to infinity of e to the j times bt, e to the at dt, and I will forget to add these things before. So in order for this integral to converge, a sufficient condition would be that a be positive, because then this term converges exponentially fast towards 0 and the whole integral can be computed. If this is not the case, then we have a big problem even defining what this means. Okay. So let's assume a is greater than 0. Then we can proceed with our integral calculation, which we resume here as integral from 0 to infinity of e to the minus st dt, and which we integrate by writing this as minus 1 over s e to the minus st dt, sorry, there is no dt, valued between 0 and infinity. At infinity, whenever this goes to 0, this whole thing goes to 0. Okay, so it becomes equal to 0 minus the value of this at 0, which is plus 1 over s. And so we conclude that the Laplace transform of a step is 1 over s. Now, we could look at other things. Okay, other examples. And the more examples we do, the more we'll understand what goes on. How about the Laplace transform of an impulse? The impulse function is a function that looks like this. If this is time, if this is the value of the function, then the value of the impulse function is 0 everywhere, except here where it becomes like a big kind of ladder and then comes back to 0. In fact, it is pretty hard to define a step, an impulse by means of a function itself. Okay, it's not really a function, it's called a distribution. Okay, and it is easier to define an impulse by its value and the way it acts on a function. The integral from minus m to m of delta of t f of t dt is equal to f of 0. Okay, so what it does, it takes the value of f at 0. Now, based on this, we can now talk about the Laplace transform of an impulse. So, the Laplace transform of an impulse is L of delta is equal to the integral from minus infinity to infinity of delta of t e to the minus st dt, which is e to the minus s times 0, which is 1. Okay, so this is the value of the Laplace transform for an impulse. We can try for a few more things, like, for example, a ramp. So let's look at that. Okay, what about a ramp? For a ramp, things will work as follows. First of all, a ramp looks like this. If this is t, if this is the value f, a ramp is pretty much 0, and then it goes up like this with a slope of 1. Okay? So in other terms, when t is less than 0, f of t is 0. When t is greater than or equal to 0, f of t is t. Now, we can look at the Laplace transform, and the Laplace transform of a ramp will be, first of all, we neglect the part as negative, because we know that f is 0 there, so it's the integral from 0 to infinity of e to the minus st times t. Now, how do we compute that? First of all, we need to have the same convergence properties such that this guy tends towards 0 when time tends towards infinity, which is not given, but as long as S has a positive real part, that works. Okay, and then under this condition, the best thing is to do an integration by part. Okay, where the integration by part goes as follows. So we start here. We write again the integral from 0 to infinity of e to the minus st t dt, and which we write as, we integrate this term, it becomes minus 1 over s times e to the minus st t taken between 0 and infinity, and minus integral from 0 to infinity of this integrated term, minus 1 over s times e to the minus st times the derivative of this guy, which is 1. Now this term will be 0 minus 0. This term is plus 1 over s times the integral from 0 to infinity of e to the minus st dt. And that term we have already computed as 1 over s. We therefore get that the Laplace transform of our delta, of our ramp is 1 over s squared. Now, this suggests something. The ramp is the integral of a step. When we compute the Laplace transform of a ramp, we obtain 1 over s times the Laplace transform of a step. Let's see how this generalizes to a broader set of functions. For that, I will create a blank sheet and restart by asking, suppose I know the Laplace transform of a function f. Would I compute more easily the Laplace transform of f prime? Now, in this case, I define f prime as df dt, and I hope, of course, it is well defined. Then I begin by computing my Laplace transform of f prime by computing it as integral from minus infinity to infinity of f prime e to the minus st dt. Okay. Again, I assume my function is 0 for for negative values of time, so I will just call this 0. Okay, and I obtain that I can compute this thing by doing the same integration by parts. Okay, I know this is the value of f e to the minus st dt. So let me say this again. Yes, e to the minus st taken between 0 and infinity. And then I will add to this, or I subtract to this, the integral from 0 to infinity of f is minus s, the derivative of e to the minus st dt. Now, this term has a particular value. That term has a particular value. Let's do a little bit of cleanup here. And let's erase these guys. Hop. Let's erase those guys. Hop. And we can write that this integral by part we can also rewrite as f of 0 plus s times the Laplace transform. Oh, this is not, yes, the Laplace transform of f. Okay, since this guy is just integral from 0 to infinity of f e to the minus st dt. Okay, so we obtain the following interesting relationship, which is the Laplace transform of f prime is f of 0 plus s times Laplace transform of f. What that means is that it is much easier to compute derivatives in the Laplace domain than it is in the time domain. Okay, in the Laplace domain, computing a derivative is just multiplying by s. Okay, and incidentally adding also f of 0. Okay, but this is much easier than doing this. For example, if I go to an example of this, what does that mean? That means that the Laplace transform, we can compute, for example, the derivative of cosine. Okay, we know that d dt of cosine of t is equal to minus sine of t. Now, in the Laplace transform domain, what is the Laplace transform of cosine of t? Well, so the Laplace transform of cosine of t will be integral from 0 to infinity of cosine of t e to the minus st dt. Now, cosine of t is equal to e to the jt plus e to the minus jt divided by 2. So if I want to compute the Laplace transform of cosine of t, what I can do is say that the Laplace transform will be the integral from 0 to infinity of e to the jt e to the minus st plus the integral from 0 to infinity of e to the minus jt e to the minus st. Everything divided by 2. Okay. And so this gives me the following expression. Integral of e to the jt, that is just integral of e to the j minus st dt, which is simply equal to 1 over j minus s. Now here, the same expression yields e to the minus j plus st, and that will be, let's see, oh, I forgot to put a minus 1 here. Okay, so it's minus 1 over j minus s, and here what we'll get is 1 over j plus s, okay, which is 1 over s minus j here, and 1 over s plus j here. Okay, and I sum up these terms to get what I need, which is the Laplace transform of the cosine. 1 over s minus j plus 1 over s plus j, and which gives us 2s over s squared plus 1. Okay, now we can so that's the Laplace transform of the cosine. Okay, so now if I erase most of what I don't need, okay, which is pretty much all that junk, why is this all one piece here? Okay, well, let me erase that. Okay, so it doesn't want to go. Alright. And that I can erase. I can do the same operation for the sinus. So for the sine, it will be, we write that sinus of t is e to the jt minus e to the minus jt over 2j, and what I will get is that the integral, so the Laplace transform of the sin is integral of e to the j minus s t plus the integral of e to the minus j plus s t, everything divided by 2j, and this Laplace transform can be computed as 1 over s minus j plus 1 over minus 1 over s plus j divided by 2j, and we can get that this will be equal to in fact 2j divided by s squared plus 1 times 2j, which is 1 over s squared plus 1. By the way, let me go back here. This is not the Laplace transform of the cosine unless we remove the 2 here. Okay? So, if we summarize the whole thing, for sines and cosines, we get a variety of interesting things. Okay? First of all, the Laplace transform of the cosine function is equal to s over s squared plus 1. The Laplace transform of the sin is equal to 1 over s squared plus 1. Now, if we are to write the Laplace transform of d dt of cosine, and we apply the rule, write that this is equal to cosine of 0, which is 1, plus s times the Laplace transform of the derivative of cosine, which is minus sine. Okay, so what do we get? We get that my mistake here, it's not that, it is cosine. Okay, so to write this, we obtain that this is so first of all, this is the Laplace transform of the sine. Okay, and we obtain that it is equal to 1 plus s times the Laplace transform of the cosine, which is s divided by s squared plus 1. Now, we get a mistake here, because that would be equal to 2s squared plus 1 divided by s squared plus 1. So where did this come from? Well, it probably came from our definition here and our findings on the Laplace transform of the time derivative. So what I'm going to do is going to set that aside for a while and start a new slide. Here's a new slide. Okay, and let us redo this Laplace transform computation. So our purpose was to compute the Laplace transform of d dt of f. we know it is equal to the integral from 0 to infinity of e to the minus st f prime of t dt. Now we integrate by part, and what do we get? That is equal to, on the one hand, e to the minus st f prime, sorry, f of t dt between 0 and infinity minus integral from 0 to infinity of minus s e to the minus st f of t dt. And so the error comes from here. This term is equal to minus f of 0, and this term being plus s times Laplace transform of f. Therefore, this minus 0 here, minus f of 0, is what led us into some problem. If we go back to this definition of the Laplace transform of d dt of cosine using what we have just said, this becomes minus cosine of 0, which is minus 1. Okay, and then there's a minus 1 here, in which case, instead of obtaining this, we obtain exactly what we wanted, which is 1 over s squared plus 1, which is indeed the Laplace transform of the sinus, as we have seen earlier. Good. So, by the way, I apologize for this mistake. I hope that you can appreciate the way I can try and recover from these mistakes. Now, let's go and talk about more properties of the Laplace transform. Okay, so let's do more properties. Okay, one thing is that if we were to take the Laplace transform of f plus g, okay, then I would notice that it becomes the sum of the Laplace transform of f and the Laplace transform function of g. Okay, and if I take the Laplace transform of lambda times f, it is lambda times the Laplace transform of f. So it's a linear transform. Okay, this is very convenient because it means that the Laplace transform of something complicated like let's see, a sine and a cosine, okay, can be computed from the Laplace transform of e to the jt and the Laplace transform of e to the minus jt. Okay. Now, there are more interesting properties of the Laplace transforms. One of them is the Laplace transform of exponentials in general. In general, the Laplace transform takes all exponentials and makes them rational fractions. Okay, so how does it go? Well, I'm going to take an exponential. F of t is equal to e to the alpha t. What I will get is that Laplace transform function, which we have already seen, Laplace transform of f, which is the integral 0 to infinity of e to the minus st e to the alpha t dt, will simply be equal to the integral from 0 to infinity of e to the minus s plus alpha t dt, which is 1 over s minus alpha. Okay, so what we see here is something very simple. Okay, let's see what happens when we mix rational functions. We mix exponentials and polynomials. Okay, so we're going to do exponentials plus polynomials. So exponential plus polynomials means things of the kind t e to the alpha t. Well, the Laplace transform of something like this is the integral from 0 to infinity of t e to the alpha t e to the minus st dt, which I can rewrite as the integral from 0 to infinity of t e to the alpha minus s t dt. Now, if I integrate by part, what I do is I take the derivative of this guy, I integrate this guy, I obtain this is equal to t over alpha minus s times e to the alpha minus s t taken between 0 and infinity, and then minus integral from 0 to infinity of t divided by alpha minus s e to the alpha minus s t dt. So if I erase all this, let me try it again. Up. Then I can take this guy and realize that this guy here is 0. Why? Because when t is 0, this guy is 0. When t goes to infinity, this guy goes down to 0. Remains this guy, which is simply equal to oh, I'm sorry. In this guy, that t should have been gone, okay, because it took the derivative of this guy. So my integration by part was incorrect. But we obtain that this becomes literally 1 over alpha minus s minus 1 times 1 over alpha minus s e to the alpha minus st taken between 0 and infinity, which also becomes 1 over alpha minus s squared, or 1 over s minus alpha squared. Now, this is exceedingly useful. What it means is that when it comes to exponentials, mix of exponentials and polynomials, okay, the Laplace transform is excessively easy to compute. We will see in the near future that such exponentials mixed with time components are very, very important in dynamical systems. Okay. Now, I believe it is important to start talking about the inverse Laplace transform. Okay. So for this, let me call my support. I never quite remember the inverse of the Laplace transform, but if I'm given a function f of s, where s is a complex variable, then I can write that the inverse Laplace transform of f, which is a function of time, is equal to 1 over 2 pi j times the limit when t tends towards infinity of the integral from gamma minus jt to gamma plus jt of e to the st f of s ds. To be more precise, this is a small t, not a big T. Okay? So t is a parameter, s is the integration variable. Okay? And so with this, we actually do compute the inverse Laplace transform. Now, that inverse Laplace transform is quite a bit more complicated to handle than the full Laplace transform. And so I just indicated to you here because it means that there is an inverse to the Laplace transform. We have L inverse of L of f, which is equal to f. Okay? So in other terms, the Laplace transform is inversible. It is a bijection. Thank you for your attention.